Hi, everyone. Shelly from Professor Paulino's research group, and I'm a PhD student, as you just saw in the 30-second. So first of all, let me begin by asking you a question. So many people have been asking the question over and over again, what does the optimal structure look like? So Michell in 1904, he wrote a paper explicitly about the optimality condition for optimal structure. Today I'm going to give you a primer on this Michell's optimality condition. And this work was a collaboration with SOM. So before I begin this talk, let me ask you another question. Why do we care about optimal structure? Yeah. Yeah. So in my opinion, yeah, I have the same opinion. So I think that the resources are becoming more and more limited nowadays, and the structures, the demand on the structures are more and more. So these are some driving forces that we found we want to have for optimal structure. And in fact, I was an intern in SOM in the 2013 summer, and what I found out is that the optimal structures are really, the designer used them to use as a source of inspirations in their creative designs. So let me begin by defining to you what do we mean by the optimal structure. So here we only consider truss members. And the optimal structure we talk about will have the minimum amount of material, the minimum volume. And so we want the structure to be satisfy some certain condition on their strength, which we can describe it in a mathematical way, where is to minimize the volume of this structure, and all the members are subject to a stress limit. But for this mathematical problem, because there are so many layouts, the solution space is infinity, so it's very hard to solve this problem. So in general, there are two ways to obtain the optimal structure. One way is an analytical way, is what is called the Michell's optimality condition. And another way is that we consider a sub-problem, and we solve using a numerical approach. And one method that is very typical is the ground structure method. So today I'm going to focus on the Michell's condition, which is the analytical way to find an optimal structure that has least amount of material. So in my presentation, I'm going to divide my talk into these different sessions. First of all, I'm going to introduce what is an optimality condition of Michell that he stated. And then I'm going to prove this condition, and followed by discussing some types of conditions types of structure that satisfy this condition, and what do they look like. And then we can, I'll introduce to you some good way to find the optimal structure, and followed by some examples of these optimal structures. So before I go into what is Michell's optimality condition, let me define to you two very important quantities. The first one is the Maxwell, according to Maxwell theorem. So by Maxwell theorem, it states that if the structure is statically determinate, and we have given set of external force, this quantity is always constant, no matter what structure you have for that given load and boundary conditions. And notice that, so this is our, what we call the Maxwell number. And this number here, the F here is the internal force for the truss member, and L is its length. So you can see that the internal force takes the sign of positive and negative. And next, let's take a look at the Michell's number. What is the Michell's number? It's the difference between the Michell's number and the Maxwell number is that here we take an absolute value. We only have the absolute value for the internal force of a truss. So this value is not a constant. And so if the structure is fully stressed, then we can show that this Michell truss has a very close relation with the volume of that structure. So we can show if by minimizing the Michell's number, it's same as minimizing the volume of that structure. Let's take a look at this example, and I will show you why these two numbers are different and what they tell us about the structure. So first, if we have these two structures that both satisfy this load condition and boundary condition, and since these two structures are externally statically determinate, first of all, then we can obtain the internal force of this truss, right? So here I'm not going to do the calculation. I list all the forces for you. And the first thing we do is to calculate the Maxwell number by adding the internal force times the length of each member. And we can see that even though they have two different structures, the layout is very different, but both of them have the same Maxwell number. So this means that the Maxwell number is really structure independent. But if you look at the Michell number, you can see that these two actually have two different numbers for Michell's number, because the Michell's number is also known as the load path and has a relationship with the volume of that structure. So later we will show you that the smaller the Michell's number, the smaller volume that the structure will have. So let's take a look at what Michell stated on his optimality condition. So while you don't have to read all those conditions, I already summarized it for you. So these conditions, what it means is that if the structure satisfies these two conditions, then it is an optimal structure in terms of least amount of material. So the first condition is that the structure needs to be fully stressed. And here we define, we need to have a stress limit on the structure. And so all the bars in tension needs to be fully stressed to this stress limit, and all the bars in compression needs to be stressed into this value. And the second condition is that there needs to be, we need to find a displacement field, and that is virtual displacement field that satisfies the displacement boundary conditions. And that displacement will generate a virtual strain for the structure, where all the members in tension needs to have a positive, has to have a induced virtual strain that is positive with this value, and also for the compression members is the same. So what I want you to notice is that here we have the strain limit and the stress limit have the same magnitude for tension and compression in this original statement. So let's take a look at how do we use these two conditions to determine what is the Michell truss. And hopefully by the end, you will know that you have better understanding of what those conditions mean. First of all, we have external force shown as here, and these three truss systems all satisfy this boundary condition and force condition, and they are all externally determinate. So you can see that we specifically choose the structure A and B to be equally stressed. So they satisfy the first condition of Michell. But for the structure C, it's not fully stressed. So because the bar in the middle here has the stress that's smaller than its compression stress. So this is not a Michell truss. And I wanted to point out one thing is that a very important thing about the fully stressed is that what does it mean if a structure is not fully stressed?
The area of some bars.
Sorry?
The area of some bars can be reduced to be fully stressed.
Exactly, yeah. So the bars, so we can always, so it means that the structure is not efficiently used, and we can always find a smaller volume by just lowering the area of that not fully stressed members. So the second condition is about the virtual strain field, and the virtual strain field has to satisfy the second condition. And here we choose the virtual displacement or virtual strain field as this, where is a uniform dilation. And we can see that by calculating the strain at each direction in this strain field, is that all the members in this strain field will stretch equally, right? Using this amount. So let's take a look at the structure A and B that we have. Since all the members has to stretch to the same limit, the structure A, there's no problem because originally, because of the force we give, it already is already in tension, and by the stretch of the virtual strain field, it is still in tension, and therefore it satisfies the Michell second condition. So it is a Michell structure. But the second one, if you can see, all the members are in tension, there's no problem. But the middle truss member, it is in compression, but this virtual strain field induces a tensile strain on that member. So this violates the Michell condition. So this is not a Michell truss. So, and if we compare a Michell truss, the volume of the Michell truss with the volume of arbitrary or not a Michell truss, we can see that the volume under fully stressed state, the Michell truss always has smaller volume. So it turns out that the Michell's original condition has some limitations because it has an assumption that your tensile and compressive strength limit are the same. The stress limit is the same, right? But it turns out that if we consider different stress limit for tension and compression, we can show that if a structure satisfies the Michell's condition, it is not an optimal structure. So here I listed the modified condition proposed by Hemp and Rosvani that, so what they did is to simply assign different stress limit and the strain limit for tension and compression. And here I want you to take a look at these two newly defined values. Both of them are positive values. So what it means is that the sigma T and sigma C are the stress limit for tension and compression. And then these quantities are the strain limit for tension and compression. They can take individual values. And let's see what it means on the structure is, so everything else stays the same except now we have different limits for the strain and stress. So now we have seen that, so what is a Michell condition and some modification to this Michell condition. And also we walk through an example of how do we determine if it is a Michell truss. So how do we know that it has least amount of material? So now let's prove if we have a Michell truss, why it has an optimal volume, minimum volume. So in this proof, I used the principle of virtual work. I'm sure that you learned this before in your class. So I just briefly stated that if the structure is externally statically determinate, then if you have a set of force, you will have your external virtual work is equal to your internal virtual work, right? If the structure is statically determinate. So here I calculate by using the principle of virtual work. Then we can see that this is our external virtual work. This is our internal virtual work for a truss member, or this is the internal virtual work for the truss member. But this external work is a structure independent. So if we have an arbitrary structure that does not satisfy the Michell condition, remember that the stress and strain inside the member, it always fall between these two limits, right? The tension and compression limit on stress and strain. So by plugging in this relation to the external virtual work and internal virtual work, we can see that the volume of the arbitrary truss is always, the volume of the arbitrary truss times this constant is always larger than its external work. But for a structure that satisfies the Michell condition, we can see that now the stress and strain is equal to their stress and strain limits. And if we plug those in, we can have that only the Michell truss will achieve this equal relation between the volume times this constant and its external work, external virtual work. So we have seen that for given a set of force, the external work is independent of the structure. But only your Michell structure, which is your lower bound, will have the least amount of material. So let me show you using the same example by using the virtual work. And just wanted to show you that the structure that satisfies this Michell condition has the smaller volume than an arbitrary truss. So what do we need to have to calculate the external virtual work? It is indeed a set of external force and virtual displacement. So by having that, so the virtual displacement is the same as the previous example, is a uniform dilation. And we can calculate the external virtual work as follows. And at the end, you can see that it really does not depend on any structure layout. It only depends on the force and the strain field. So for the same two structures, one is an arbitrary truss and one is a Michell truss, we can see that we already have our external virtual work. The internal virtual work, if we plug in to this expression, we obtain the same internal virtual work, which makes sense because both of them are statically determinate. So these values should be the same. But if we calculate the volume of each truss, if they're they are fully stressed, then we obtain that this volume for the Michell truss always smaller than the arbitrary truss. And let me ask you a question. So I've sort of asked it before, is that what happened to this volume of this arbitrary truss if it is not fully stressed? Yeah, it will only become larger. The volume will only become larger. So this is really your lower bound for the given set of force. Let me summarize what we have seen about the Michell's condition. So first of all, we use the idea of external work is independent of the structure, and therefore we obtain that the volume of our Michell truss is the lower bound. It has the least amount of material. So what I wanted to point out is that the Michell's optimality condition, it is a sufficient condition for a truss to be optimal layout. And so the procedure of finding the minimum volume of a given set of force is as follows. First, we need to find the virtual displacement that satisfy the Michell's condition. And then we have this very important feature for a Michell truss is that all the members, the truss members of the Michell truss must lie on the principal direction of that virtual strain field, because the principal directions gives you the largest strain and the stretch, right? And if we have the external work and the virtual displacement field, we can just calculate our Michell truss volume by using this expression. And these two are the positive numbers that we assign to the structure. And later on, you will see that these two terms will vanish. It only depend. This one will vanish. It only depends on the maximum stress limit you assign. So we have seen how do we identify a Michell truss and why it has the least amount of material. Let's see, and the natural question to ask is that what does it look like? So what does the structure look like? So next I'm going to talk about some types of structure that satisfy this condition. The first type is a very simple type structure, which is if the truss has members, all the members are either in tension or all the members are in compression. So automatically, this type of truss will satisfy the optimality condition if it is a fully stressed structure. And so the virtual displacement field here I listed only for the tension-only case, where you have your virtual strain field in the principal direction, and in the principal direction have these two strain limits. And then by doing some integration or solving the PDE, you can obtain the displacement, virtual displacement for that virtual strain field. And if we have the virtual displacement field, we can calculate it using this formula. And they always have, so both of the structure are the structure in this type, and both of them have this expression of this volume. And this volume depends on the location of the location of your force, X and Y here. The second type is a little bit more complicated. It is essentially the truss member that, what it says here is the second part of the condition of Michell truss. So what it means is that the bars must lie on the principal strain directions if it is an optimal structure. And so because of the principal strain direction are always orthogonal to each other, then we have the conclusion that the tension members and compression members, if they intersect, they need to be perpendicular to each other. And this condition needs to be met for both before we apply the virtual deformation and after we apply the virtual deformation. So in order for the strain field to still be orthogonal after the virtual deformation, we need to satisfy this condition, which is the compatibility condition for a virtual strain field. So what it really means is that if we connect the direction of a virtual strain field and virtual strain field in two directions, one principal direction is this, and the other principal direction is this. We obtain this curvilinear orthogonal coordinate. And what it really means is that for a given series or the given alpha lines, this change of the slope needs to be constant along this beta line, along the other direction. So those are just some compatibility requirement for the strain field. So now let's see sort of some of the fun stuff. Then how do we use the Michell condition to find a Michell truss? Here I will give you some examples of the coordinate that we can use to construct an optimal layout using the condition. So it turns out that those curvilinear coordinates, the curvilinear orthogonal coordinates, are also called the Hencky nets. The Hencky nets is basically the orthogonal curves that's satisfying the compatibility condition that I just introduced. And usually the Hencky nets are very complicated, and if you wanted to explicitly express the strain field for that Hencky net, it's not very easy. But there are some simple ones, and I listed here. Some of them are so they are Cartesian coordinates, polar coordinates, and the combination of Cartesian and polar coordinates. And another Hencky net in the simple form is called Equiangular spirals. I'll show you each of one right after this. So here, I wanted to reinforce the idea that the procedure of how do we find the virtual displacement. So first thing we need to do is to recognize the Hencky net we want to use, and then we obtain the virtual strain field from that Hencky net. Usually those virtual displacement field, the virtual strain field from the Hencky nets are written in some coordinates, for example, the Cartesian or the polar, which you already have. And then the second thing is to get the virtual displacement field, which is to solve these PDEs. And this is an example of the PDE for Cartesian coordinates and the example for the PDEs in the polar coordinates. Because you know that the value of your strain needs to it needs to be the same as the strain limit that you put for the structure, and the direction of your virtual strain field needs to be lie on the direction of your principal strain, or the coordinates axis of your coordinate that you choose. The first type is the Cartesian coordinate. So we can write this orthogonal, so it has the orthogonal parallel straight lines that one direction it indicates the strain field in tension, and the other direction indicates the strain field in compression. And so by solving the PDE in the Cartesian coordinate, we can obtain the corresponding virtual displacement field. And as you can see that the virtual displacement field, these terms are the rigid body motions of the structure, so it does not play a role in the strain or the deformation of the structure. And the second type is written in the polar coordinates, where you have one virtual strain direction pointing at this direction, radial direction. The other direction is your tangential tangential direction. And again, solving this PDE in the polar coordinate, you obtain your virtual displacement field as follows. And another example is to combine the polar coordinate and the Cartesian coordinate. And the only thing you need to be careful is wherever these two coordinates coincide each other, you have to make sure that they are compatible, which means that the displacement here of this Cartesian coordinate and this polar coordinate needs to be giving the same value. And here I just show you what I mean. So here this is the polar coordinate of this type of Hencky net. And it's essentially the same with the one that I showed earlier. And the second region where you have the translate Cartesian coordinate, you need to make sure that, again, this part is compatible with the polar coordinate. And what you need to do is when you solve the PDE, make sure the rigid body rotation part is calculated correctly. And another type of a Hencky net is the equiangular spirals. So what it means is that the set of spiral in one direction indicates the principal strain in tension, and the other side of the other direction of the spirals indicate the principal strain in compression. And we have assumption here is that the tension limit has to be equal to the compression limit for this spiral. So now we've seen some of the coordinates that we can use, or the Hencky nets we can use to construct optimal structures with minimum volume. Then let's see some examples of the Michell truss. And here I show you some 2D example of some Michell structures. And so today I'm going to show you the very simple derivation of these two structures. So for this given set of boundary condition and load, we wanted to make use of the polar coordinate in this case. And we can see that all you need to do is, we already obtained the virtual strain field in the polar coordinate. And now what we need to do is to just plug into the external virtual work. One term, so one thing is your external force, the other thing is your virtual displacement field at this point. And by plugging that to your virtual external work, you obtain this. And by dividing this positive value, you obtain that your minimum volume for this kind of Michell truss is in this expression. So here I wanted to point out that in this problem, you can have different value on your tension and compression stress limit. And so one thing I want to point out is that in the previous problem, I subject the design space as the top half or the semi-infinite of the design space. And now here is the same force, external force, but the design domain, I set it to infinity. So it's anywhere along this plane. And now we make use the Hencky nets that combines the polar and the Cartesian. And as you can see, you can, the only thing you need to be careful is that you need to have the virtual strain and stress principal values in these bars that you will have on your optimal layout. And all your members need to lie on the Hencky net. So if we lower these two forces, we can see that we can still make use of this Hencky net, and we obtain the minimum volume of this value, and by just so here is a difference between the volume here and with the previous one. And if we further lower these two loads, we can see that eventually we go beyond the this Cartesian coordinates, so we only make use of these polar coordinates here, and the minimum volume is as follows. So now let's take a look at some 3D Michell truss examples. One very famous one is a torsional ball. So I wanted to point out here the proof I'm giving today is a partial proof, because in the original Michell paper, this torsional ball is derived with this design space that is infinity. But here I need to I do a partial proof where I restrain the your Michell truss on this sphere. So this is just some my thinking procedure of how I make use of the strain field that I chose. So first thing I did was to cut this sphere from this direction, and we can see that these two lines, we can express it in terms of the radius and the sine of this angle.